All right, so I'm going to talk uh, mainly about images in particle physics and nanotechnology. Um, Basically, how kind of the political status of them is, or socio-political status of these images are. Besides their evident scientific technical power, right, and their explanatory power, because we're constantly provided with images in the press and in the media of various phenomena that are supposedly happening at a very small scale. For example, the quantum chip or various particle physics phenomena like the Higgs boson, which are presented in magazines and websites and such. And they have a particular pedigree and a particular use. Oh, fantastic. So here we are. Let me try to get the slideshow working. It's coming. As you can see, this computer is of the older generation. Its chips have been worn down by many interesting activities. Well, I'd have to transfer everything onto yours. What happens if I? Oh. It won't last that long this time. It's not used to HDMI. Here it is. Okay. Yeah. Oh. Okay. Now where's the image? Oh, there it is. Okay. Good. Okay. So this is the title. And thanks to Isabel Schrickel, who's not here anymore, I guess. She had to get going. But she provided this nice image at the to the Facebook page. So if you go to the Variable Worlds Facebook page, you'll see this neat image, which from the 50s or 60s, where they're showing how simulation and also especially like quantification plays into let's say a technological understanding of the physical world, the non-technologized physical world that we experience, classically, empirically, right, with our bodies. So you can see here, well, you got the physical simulation, you got a theory, and the theory becomes a mathematical model. Mathematical model is supposed to encapsulate the theory. You got the observations, and then does the the mathematical model fit the observations, and then you get the Nobel Prize there as a little certificate on the side. Right, the guys I was joking about, but it's not a joke. And yeah, okay, so you get algorithms that, nowadays more advanced modeling involve algorithms and computer programming, punch cards, well, more advanced things. Anyway, and it all functions in. The most important part of it is, of course, that computer simulation, all computer simulation, is calculation of variables. Variables usually inputs, sensor data, eventual sensor data, according to theoretical mathematical models. So we're in a highly quantified space. Of course, this leads to what also Andreas mentioned, Dr. Andreas, the theory of everything, kind of a all-encompassing theory of the physical material world, which takes a kind of bottom-up approach, or at least from isolating certain fundamental elemental particles, we will be able to kind of rebuild the way things manifest themselves to ourselves, including ourselves through calculation. Of course, Einstein was critical of that, and Stephen Hawking also did kind of cast some critical side to that, is that it will always be an equation. So inside this kind of quantified space, we're always dealing with equations where everything will equal something. So there's a there is something that has to be on one side of the equal sign and on the other side, and in the end, it's just 1. Okay, so here's this is not the CERN, although it says CERN there, but this is at the Frankfurt Book Fair, where the CERN had a booth to show that they also have they're releasing some books of the incredible visualizations that they do produce at CERN, which are really fantastic. And there's also there's actually a book of photography of the inside of CERN, which was it's endlessly fascinating. I'll probably knock that over, by the way, Sasha. As part of their display there, they also had some visualizations with pretty, customary visualizations of particle collisions there, where you see lots of things flying here and there, and it's very stimulating and exciting. It's you get this sense of power too. It's like a mini star that they're creating inside there. The power that we're mastering 100 meters under the ground at 1.9 degrees Kelvin, which is colder than outer space, by the way. The conditions under which the particle collisions take place does not even exist in outer space. We're actually creating some things which are even beyond what we have been able to experience having traveled outside the stratosphere. But as you can see, that these are very important parts of the display. It's somehow demonstrating to the general public that there is some kind of mastery going on, that we actually know what we're doing. And how do we know what we're doing? And well, we have lots of calculations, and as Andreas said, it was pretty amazing that according to, after having done all the simulations to build the LHC, they actually did generate the particles, or at least phenomena fitting the model of the particle that they were looking for. So, and actually, the particle accelerator did produce the luminance, the speed, energy in the chamber that would produce that phenomena. Okay, so but the phenomena, of course, we're looking for is the Higgs boson here. It's a new element. This is the standard model of these building blocks. They really are building blocks. I mean, it's a very abstract model of the universe, but yeah, that's all there is. There's just some green squares, some blue squares, and some pink squares. You add them together, and you get me and you. So yeah, and these green, blue, and red squares are all produced here originally as we get closer to the supposed Big Bang. That's why it's high energy physics, because the highest energy is there, right? We're getting closer and closer to the super high energy of the supposed Big Bang. We got that way by calculating a lot of decay patterns and chemical spectra from the existing planets and stars that are in our neighborhood right now, as well as the chemicals that are on the Earth now. And we kind of hypothesized backwards to an original place where all these things were generated, according to mathematics. It must be there. Of course, these things that do not really have any particular image. They are just mathematical objects. And for example, this is a boson, Z boson. It's not the Higgs boson, but this is a boson in the kind of graph language that the scientists use, which you don't usually see at the Frankfurt Book Fair or those kind of places. So, okay, one principle, one axiom I will put here is that science is no longer about the search for truth. It is about reproducing repeatable results, and that's something that I think you can tell that we've actually lost sense of that. What like Leucippus or Democritus were going after when they were meditating in their agora, or not their agora, their domus, or their school, or wherever they were sitting around thinking about the universe with their students. They were looking for some essential thing, and we're in science today. We're not really looking for that anymore. We are looking for we create models, and we try to generate results that fit the models. And if we do that, then we have a proof, so to speak. And the reason that's very important is because it leads to industrialization of new technologies. Andreas showed this image. This is the CERN. It's underground. Part of it's in Switzerland, and part of it's in France. A very small part's in France, but they had some nice treaties. I have a nice picture here of the. Which one is it? This one? Okay, I have to reframe this. This is exactly how it looks like inside the. Yeah. Okay. Oops. Yeah. Starting the game. Yeah. You can win. If you win the game, you get. You see, they have even the formula on the side there, the mathematical formula of the Higgs boson. Sorry, it's like catching a bit. It's actually a big file. It actually took 17,000 computers 5 weeks to make this. No, I'm just joking. Sorry, it's like sticking a lot. It's like much too powerful for my computer. Okay, there it goes. No, I can't. You see, it went through the border. Now here are some particles. That's what they look like, actually. Actually, particles are not round. By the way, they actually don't have any shape at all. They're if you ask what okay, I'll explain that after. And here we go into this nice 3D thing of the Atlas detector, where Dr. Andreas is working. Okay, and you can guess what happens next. It's this, right? Yeah, of course. The computer breaks down, and yeah, you know, it's terrible gray goo. You know, Eric Drexler, the gray goo. Okay, I'm running ahead. So that's what's happening under here. Right? You got it? Very exciting. Okay, so anyway, they speed around in there, and then at certain points, there it says Alice there, CMS, they reach each other and create new particles with very high energy. That's the reason why they had to build the LHC, is because the energy was not high enough to... Okay, so then, good. How do they find? Oh, they're looking for the Higgs boson again. I don't know if I should risk even like going full screen. Might take forever. Okay, so yeah. Okay, so you got the. How can they find it? Well, you know, they have various layers. Andreas showed this a bit. At the center there is where the particles are created. The new luminous particles, the results of the collision. They go through various layers of detectors. Here we have the hadron calorimeter, which is a made up of all kinds of copper and lead and a lot of liquid argon. Then we have the muon chambers over there. Anyway, the particles go through there. They interact with, you see, because we can't get any data out of them unless they interact with something. I mean, it's completely dark down there. It's very cold. Nobody's down there. And we need to get some, data. So we need some materials that the particles interact with. So we put all kinds of particles down, all kinds of materials down there in layers. And as the particles interact with those things, they either they themselves send a electronic signal to the computer, or they send, like if they're electronically neutral, they go through some various other tricky things, like in the calorimeter, like the liquid argon, which produces a photo charge, which is then detected and turned into electronics. Everything has to be turned into electronics to be calculated. That's why we only have an electronic model of the world, because we that's the only thing that we really do master is electronics. Yeah, this is actually how the liquid argon calorimeter works. You got a scintillator here, where the light is produced with liquid argon, and then you have like the light is amplified, and electronic signals produced and sent to the computer. Okay, this I'll skip, but Brigitte Falkenberg is a really good person to read, especially this book on particle metaphysics. But basically what she's saying is that the models that we create in the quantum physics and the quantum mechanics world are not compatible with even our language. We have a language that's kind of built on a classical physics model, and we always have to make that translation. So there's a lot of translation missing. I see that I'm already at 15 minutes, and I guess is that wrong? Okay. Oh, okay. Oh, you're being lenient with me. That's very kind. Anyway, I just skipped to another kind of funny document just to show you. what I mean with the electronics of this system. It's quite, yeah, this is fantastic. Okay, so what it is inside the atlas, exactly like the Hadron Calorimeter, I don't know how to pronounce that, you just have repetition on repetition. It's grids on grids on grids of actual materials. It's not grids of like computer grids. These are real made grids of like copper tubes here, and they're all going to be filled with liquid argon. It's fantastic. Can't wait. Come on. I don't know. Oh yeah. Okay. Now here they are. Oh, a little bit more. Matrix stacking of the hadronic FCal module. Here we go. Okay, here's the liquid argon. They're sticking the, I don't have the picture of the liquid argon tubes. No, I skipped that. But anyway, you can guess that in these little holes here, there's little holes, all these holes in the grid. They're sticking in these very thin tubes of liquid argon. Fantastic product. And then, here we go. This is the exciting photo. Come on. They're at the hair salon. No, they're not. It's not the hair salon. But they're completing the thing. Well, it's a highly precise thing. You don't want to get your whatever. What is it? Schuppen. Your dandruff in there. And as you can see, okay, they got it all together finally. I mean, it took forever. And then they got all this spaghetti coming out. The hair, which is the cables, right? The electronic cables. So this is just one of the detectors. But, you know, each little tube, each little element has to have one little cable coming out to the sensor array, to the grid where the modeling can take place. So it's not like it happens like mysteriously. There's no connection to the computer. It's not happening by wireless. No, everything has its own cable. It's a very hairy beast there. Look at that. Isn't that amazing? I don't know if that's how they finished with it. Kind of looks like a, I don't know. You tell me what it looks like. Okay, so where am I back? I'm back here again. Okay, the reason why we get how we got here is that we standardized the material. So the copper, the liquid argon in there, the lead, everything in there is highly purified material. That is like, it's not the lead you find in the ground, it's not the copper you find in the ground. It's gone through all kinds of processes to be very pure, atomically pure, so that it behaves reliably when subjected to certain conditions. That's how it all works. So first we have to purify things to almost an absolute state. And then we start to get reliable results. And that was like, I would say probably Lavoisier is the one who really like brought it on full time, you know. Lavoisier is the guy who disproved Priestley's phlogiston theory of how that there was this thing in the air called phlogiston, which was the fire thing. He found that there was just oxygen and hydrogen producing water without any phlogiston. He had like big vats of oxygen. He weighed it, and he weighed the hydrogen, and then he put them together, and there was a spark, and then he made the water, and he proved that and he could repeat it over and over again. Like, look, I have, you know, was it 2 volumes of hydrogen, 1 oxygen, and here's the spark again. I get this amount of water. He did it over and over again. That's like basically the incipient moment. Rutherford took it further, developed the atomic model further, and we got to understand like how materials work like that, but only with very extremely pure materials. Okay, so nowadays we have like in things like in things like the LHC, we have incredible buffet of exotic materials here mixed together in incredibly sophisticated ways. It's a Feinschmecker, metals Feinschmecker's paradise here. And let's not forget that the Lavoisier discoveries and the refinements were part and parcel with the beginning of the age of imperialism and the scramble for Africa, where a lot of these materials are taking place. I won't harp on that, but I'm missing that one slide. But let's just say that that colonialism hasn't stopped. We're still dependent on materials from there. So are the Chinese, and The whole industry is based on that now. You see, I got to the political part and it wants to stall. Okay, yes, here we go. I even missed it. So, okay, so how do we know? Well, there's a guy on a Windows machine, or many Windows machines, checking his email, and he gets the email and he says, "You won the Nobel Prize." And okay, then again, what Andreas said, it takes enormous amounts of computer power. This is one of the computer banks that CERN, I think it's not at CERN, but it's in Switzerland. This is at CERN, right? Yeah, so I mean, it's like enormous amounts of computers which have to produce I have it here. All proof of the understanding of these perfect materials. The fact that this computer kind of works, this one works better, is a fact that we really do understand how these materials behave down on a very infinitesimal scale, on a nanometer scale, because they're working, they're processing, they're producing this image. Otherwise, they wouldn't work. So these computers do prove our mastery over that. But, of course, the LHC was supposed to cost 2.7 billion euro. Instead, it cost almost 300% more. I asked the question, why is it easier to calculate how much Higgs boson than the construction budget? Which you would think, like, it's all people, you know, and things. So why could they construct make the construction budget properly? Well, the point is that the LHC, besides producing Higgs bosons, is actually a huge make work and construction and industrial incubator. It produced a lot of work for scientists, but not just for scientists, construction workers, various people. This is actually Furukawa Electric, who produced the superconducting cables for the cryogenic magnet array, which is necessary to speed up the particles very fast. Special titanium. I forgot what the other thing in the alloy is. But anyway, special cables. They of course, hundreds of people work there. Baudrillard, because we were talking about simulation, you know, brought Baudrillard back. You know, he's saying, like, of course, he's talking about the use of simulation as a kind of political tool, in a way that, you know, the mass media event kind of influences all of us, and we can't see out of it, and then we lose our political perspective. Of course, so we live in this desert of the real, which doesn't really have any political status, but nevertheless, we're still sitting here, and we do have political status, though you wonder what we should exercise it on. Okay, so we have like images like this, and it says like, okay, this is, you know, this image is like the most high resolution. You see that on Facebook. It's the biggest high resolution. There's a new one now, but this was like, I don't know, 6 months ago. The biggest high resolution image of the space that we ever got, you know. This, the detail was like 10,000 pixels, I don't remember. Anyway, but you can see like it's actually a very small section of space. It's actually just this amount here. So if we would have to observe the whole sky, it would take 1 million years. But that'll do, you know, to impress people. But, you know, that's the kind of Baudrillardian simulation that we're talking about. This is actually the one of the cameras inside the Hubble telescope. You can see it has a CCD here and another infrared detector here, and you know, it's just bringing in light photonic waves. Of course, that's not even one image. It's actually the produced from 3,012 images by this guy, Dr. Anton J. Kukamur, who had to work really hard to figure out how to put all those things together in Photoshop. Okay, but the Hubble CCV, of course, we saw this image before here, is an industrial product like any other. You know, it's a nano level pixel array. Produced, you can see it's very regimented, because everything inside computers is regimented. There's no freedom in a computer. If you have freedom, you know, be happy, because like computers, no. And like anybody who's like, making a computer, no. People making computers, if they have freedom, computer doesn't work. So here's I want to just point out that, you know, all this stuff has, like, you know, important industrial and kind of social dimensions. The Hubble telescope, well, it's pretty big. Also, that had to be built. It kind of looks like it's made out of tinfoil. Also, incredibly over budget. Incredibly over budget. I can't calculate that. Bring Flusser in there. A little moment of Flusser. He's just saying that if you look closely enough at the photograph, then you will notice that it's even more coded. And in a sense, what Flusser's saying here is that the photograph, what he's talking about, photograph like the chemical image made up by the history of Western science, we call Western science, which produced the chemical mixtures which are put on the paper, exposed to light, whatever. The history of Western science that is evidenced in a photograph is the real message of the photograph. And that's the code we have to look at to understand what the images are saying. Here's a nice simulation. Voyager probe leaves the solar system. Of course, that's not the solar system. That's if you look carefully, it's an artistic rendering. You see a lot of those. And of course, the very important that a new space agency will, of course, seeing that we're having so much success, we're going to have 100,000 jobs within 20 years in the UK space agency. I don't know if that's actually started yet. Okay, last example, we have the famous IBM spelled out with atoms. This is a image from Don Eigler from the early 90s. He individually manipulated these atoms on this surface here. Surface is nickel. It's very funny that there's this surface supposed to be nickel, but it doesn't have any atoms. I don't know why. Anyway, just the xenon atoms. The xenon atoms are obviously much bigger. And of course, atoms look like, I don't know, Hershey Kisses, you know those chocolate? I don't know why they have that shape, because of course atoms do not have a shape. They have some electrons, which maybe you could generalize and create that shape if you put a long exposure camera on it. Anyway, he did move them, and of course he thanked his sponsors well for that. Now we have these kind of machines which can do the same thing. Again, we have some kind of like hillock-shaped atoms. I don't know. They're not really accurate. Okay, that's what I wanted to say, just to make sure that, okay, this is the, just for scale, this is one of the parts of the CMS at CERN. And this is the size of a muon that it's supposed to detect. So this thing is the muon detector. It's n times 10 to the minus 33 centimeters squared. Compared to all those people who had to build it, it's very small and compared to the people who had to build it there. I think I wanted to play you one more video if I can. Is that all right? And that's it. I'm gonna let you go. Well, my playlist is gone. All right. Well, I actually wanted to ask you to ask me questions during the talk, but now it's already at the end of the talk, so maybe somebody has questions. Thanks for your attention.